What we're going to do now is calculate the gravitational force of a sphere. And how we're going to do this is assume that Newton's law of universal gravitation, F equals G m1 m2 over r squared, holds for point particles. And we're going to show that if this holds for point particles, then it also holds for spheres. And in that case, we can model all the mass of the sphere as being at the center of mass of the sphere. Okay, so let's start with our sphere. And we'll start with a mass over here with mass m, and what we're doing is eventually we're going to be calculating the force of this sphere due to gravity on this point mass m here. So let sphere have mass m, but what we're going to do is break our sphere up into onion shells. So I've drawn the first of the onion shells here. Consider a spherical shell with mass dm. So there will be other shells as well, and we may say the total sphere, for example, could be this big, but we're only considering one shell at the moment. So let's take the distance between the center of our shell and our point mass over here, m, as little r. And we're actually going to have to break our shell up. So let's start by considering a little ring. So we're going to call this angle here theta, and then we'll take a ring all the way around our shell. So this is a circle. Our shell has a radius capital R, and we're considering just the part of it between theta and theta plus d theta. So this little width in here is d theta. So we're going to start by considering the force on m from a little point up the top and a little point down the bottom around this ring. Now, gravity is an attractive force, so we have a force up towards this point and also a force down towards this point. And hopefully from that little diagram you can see if we call this angle in here alpha, then we can break this attractive force up into a vertical component and a horizontal component. And with these 2 points on opposite sides of our little ring here, the vertical components are going to cancel out and the horizontal components are going to add together. So we can do that for any pair of points around our ring here. The force towards the center of the sphere will add together, and the forces perpendicular to that are going to cancel each other out. So considering just these horizontal components that add together, we can say that the force due to the ring is equal to the universal gravitational constant times the mass of the particle here times the mass of the ring. Now we need to divide by the distance between the ring and the mass m. So let's give that a name. Let's call that length s. So s is that distance. This distance here is also s. So this is divided by s squared. And then we're only adding the horizontal component. So then we multiply it by cos alpha, where alpha is this angle in here. Okay, now we're going to want to simplify this a little bit. So let's start by calculating dm ring. So physically, this is the mass of this ring here. So we can calculate it by calculating its area and calculating the surface density. So the area of the ring is equal to, well, the circumference of the circle. But when we're considering that circle, the radius of this circle is given by looking at this triangle here. The hypotenuse is r for this spherical shell, and this is given by r sine theta. So the radius of the ring that we're looking at is r sine theta. So the area of the ring is given by the circumference, which is 2 pi r sine theta, times the width of the ring. So this subtends an angle d theta in here, and we know that arc length is given by r d theta. So the width of our ring is given by r d theta. So this tells us that the area of our ring is equal to 2 pi r squared sine theta d theta. And now the density, the surface density, which is equal to the mass over the area. Now we've said that the spherical shell has mass dm, so that's dm, and the surface area of a sphere is given by 4 pi r squared. So we can now get dm ring as the density times the area, so that's 2 pi r squared sine theta d theta times dm, and we're dividing by 4 pi r squared. So these r squareds cancel, the pi's cancel, one of these 2's cancels, and we end up with this is equal to sine theta d theta times dm over 2. So now we can substitute in this into this expression here for m ring. So this is equal to gm times dm ring, which is sine theta d theta times dm, and then we've got the 2s squared on the bottom times cos alpha. So this, remember, gives us just the force due to this one ring. Eventually we're going to need to sum all the rings over this sphere to get the total force from the spherical shell that we're considering. But for now, let's have a bit more of a look at this cos alpha term and how alpha is related to s and our r's. So to do that, let's draw out this triangle a little bit more neatly. So this length here is s, this total length along here is r, this one here is capital R, the radius of our spherical shell, and then we said this angle here was theta, and this angle in here was alpha. So you can see this length here, just by considering this right angle triangle here, is given by r cos theta. And this height here we've already said is r sine theta. So we can see with this triangle here, this length here is going to be r minus r cos theta. So using this triangle, we can write cos alpha is equal to adjacent, which is r minus r cos theta over s. So that's one expression for cos alpha. We can also consider this big triangle here with this angle theta in here and our cosine rule and write, well, s squared is equal to r squared plus r squared minus 2rr cos theta. So now we can rearrange this equation to write, well, minus r cos theta, which is here, is equal to s squared minus r squared minus r squared. and then we need to divide by 2r. So we can now substitute this into here, replacing this part, which is equal to r plus s squared minus r squared minus r squared onto r divided by s. We'll multiply the top and the bottom by 2r on 2r. So this is equal to 2r squared plus s squared minus r squared over 2rs, which is equal to r squared plus s squared minus r squared over 2rs. Okay, so now we've got a simplification for cos alpha. What we want to do now is try and replace this sine theta and d theta somehow. So to do that, let's have another look at this equation, and let's actually differentiate this equation with respect to s. So if we differentiate both sides of this equation with respect to s, we've got d of s squared ds is equal to d of r squared plus r squared minus 2r cos theta ds. And so this is 2s, which is equal to, now the radius of our spherical shell and the distance between the center of the sphere and our mass m are not dependent on s. However, theta, this angle in here, does have a dependence on s. So let's use the chain rule here. Let's go, this is d r squared plus r squared minus 2r cos theta d theta times d theta ds. And so differentiating this with respect to theta, we end up with r squared, and r squared are independent, so when we differentiate them, they're 0. And now we're differentiating minus 2r cos theta. So when we differentiate cos theta, we get minus sine theta. So the negatives cancel out, and we have 2r sine theta, and then d theta ds. And that's equal to 2s. So you can see the 2's will cancel out, and we end up with an expression for sine theta d theta is equal to s ds divided by r. And that was useful because we had a sine theta d theta up here. So now what we're going to do is replace the sine theta d theta with this expression. And we're also going to replace the cos alpha with this expression here. So we can write this as gm dm over 2s squared times s ds over r times r squared plus s squared minus r squared over 2rs. Now let's simplify this as much as we can. We've got an s on the top, an s on the bottom. We can put the 2's together, so we can write this as g m dm over 4 s squared r squared, and then we've got r squared plus s squared minus r squared ds. Okay, so that tells us the total force from this ring here is an attractive force, so it's going to be to the left on this mass here. But now what we want to do is sum up all those rings across the entire spherical shell. So we want to go from sum from theta equals 0. So theta equals 0 is here. And so you can see at theta equals 0, we have the relationship between r and s that S, this length here, is equal to r minus r. And then we want to sum up all the rings round to here, which is theta is equal to pi. And at this point, we've got that S is equal to r plus r. So now we're going to integrate. When we sum all the contributions on the left-hand side, rather than having the force due to one ring, we have this force due to a spherical shell. And we're integrating from r minus r to r plus r of gm dm over 4s squared r squared times r squared plus s squared minus r squared ds. Let's pull all the constants out the front. Let's just put that in a little box because we've dealt with that bit. And so we've got g m dm, and then here we've got 4r r squared. And now we're integrating from r minus r to r plus r of r squared minus r squared, and this is over s squared plus s squared ds. Okay, so let's split this up. We can put this is over s squared and this is over s squared. So in here we've got r squared minus r squared on s squared plus s squared on s squared, which is just 1. So we're now integrating gm dm over 4r r squared from r minus r to r plus r of r squared minus r squared over s squared plus 1 ds. So integrating gm dm over 4r r squared. Now this is r squared minus r squared times s to the minus 2. When we integrate that, we end up with r squared minus r squared times s to the minus 1, and then we have a negative sign out the front. And when we integrate 1, we get plus s, and that's from r plus r to r minus r. And we know that we can write this as, instead of s to the minus 1, divided by s. So I'm going to write it that way now because that'll be a bit easier. Okay, so let's substitute in our limits now. Okay, so let's expand this bracket as r minus r, r plus r, and then I'm substituting in r plus r for my s on the bottom. And I've got plus r, and now minus, so that becomes plus r minus r, r plus r, over substituting in r minus r. Okay, and then we do minus s, substituting in r minus r, so that's minus r plus r. So now I've cancelled out common terms between the top and the bottom. Let's evaluate this. Got gm dm over 4r r squared times minus little r plus big R plus little r plus big R. So you can see those two cancel each other out. And I've got this one plus little r plus big R minus little r, which will cancel that little r, plus big R. And so I've got 1, 2, 3, 4 big R's. So this is 4R. So you can see I've got 4R here and a 4R there. So those will cancel out. And I'm left with gm dm over r squared is the total force from that one spherical shell. Now, if I want to get a total sphere, solid sphere, I need to add all the spherical shells. Now, these are all directed towards the center of the sphere there. And r is the distance between the center of our spheres and our point mass m. So this doesn't change for the different spheres. So if I say that the mass of my total sphere is the sum of the spherical shells, then all I need to do is replace this dm with this m. None of these other terms change. So the force from the sphere is just equal to gm times m over r squared. So now we've proved the shell theorem, and it's fine to go ahead and assume that for spherical planets, we can just model them as point particles with all the mass centered at that point in the middle. So we've seen what's happened when the point mass m is outside of this spherical shell. But let's see what the gravitational effect is if we instead put the point mass here inside this spherical shell of mass. So to keep it neat, let's draw another diagram here. This shows our spherical shell of matter with a total mass dm around that sphere. Here's the center of the sphere. Our little mass m is here, and the distance between the center of the sphere and the mass m we shall still refer to as little r. And we're going to consider the same ring as we had before. It's a radius r away from the center of the sphere, and it's got the same width and area, and we've got the same angle theta here. And s is the distance of the mass to that point on the edge of the ring. Now, looking up at this equation here, almost everything in this equation remains the same. There's nothing which is going to affect the mass of the ring, so this sine theta, d theta and everything is still the same. What's possibly changed is this cos alpha. So alpha is this angle here. And let's just draw this triangle one more time. We've got the radius r along there. We've got the distance little r along here to our point mass here. This is length s, and this angle in here is alpha, and this one's theta. And our reason for finding this alpha before was because if we considered points on opposite sides of the ring, so up here and down here, then the forces, the horizontal components, which multiply by cos alpha add, and the vertical components subtract off. So that's still the case. So we're still going to want to find this cos alpha of this alpha here. So we can write cos alpha. Now we're considering this triangle here. We've got side S here, and this side is going to have length. This is r cos theta. So this is going to be r cos theta minus r. So r cos theta minus r over s. So you can see before it was r minus r cos theta on s. So it's almost the same, but it's got the opposite sign to before. And then using the cosine rule, we've still got s squared is equal to r squared plus r squared minus 2r cos theta. That's still the case, which means that all this taking the derivatives and getting sine theta d theta is equal to s ds on r is still going to work. We'll still be able to make that substitution. But what we will need to do is change this a little bit. So we can now write this as, so now for r cos theta, we rearrange this and we get this is equal to r squared plus r squared. And then we're subtracting s squared. And then we need to divide by the 2r. So we multiply by 2r over 2r on both the top and the bottom, and we end up with r squared plus r squared minus s squared minus 2r squared over 2rs, which is equal to r squared minus little r squared minus s squared over 2rs. So we've now got a slightly different equation for our cos alpha, because our alpha is a little bit different inside. Now what we're going to want to get is the force from the spherical shell once again. We can substitute in this for the ring, so we have our expression for the ring. And so let's look at the limits on our integral. When theta is equal to 0, so that's along here, we can see that s is going to be equal to r minus little r, so big R minus little r. And then when we've got theta over here, pi, in that case, s is going to be equal to big R plus little r. So let's now substitute into here just like we did before. The differences are now the limits and the sign. You can see that this has got an opposite sign to what our cos alpha did before, but everything else is just going to be the same. So let's write that down. We've got f for the shell is equal to, so because it's the same, I'm going to pull the same common factors out the front, gm dm over 4r squared. Now my limits are different, so I've got r minus little r, and I've got big R plus little r, and then I've got my big R squared minus little r squared over s squared. That's this one, and then this one I've got a minus s squared on s squared, so minus s squared on s squared ds. So now I'm going to integrate this, and I get gm dm over 4r squared, and integrating this I get minus r squared minus r squared, and then this was s to the minus 1, but I'm putting the s on the bottom, and this is just 1. I've got minus 1, which I'm integrating, which gives me minus s, and that's from r plus r to r minus r. And now I'm going to substitute in, so I've got gm dm over 4r squared. Okay, now this I can write as minus r plus r minus r over r plus r, so minus r minus r, and then minus r plus r, and then I've got plus, and now I'm putting in r minus r plus r over r minus r, which gives me plus r plus r, and then I've got plus r minus r. So this is equal to gm dm over 4r squared, and then I've got minus r plus little r minus big R minus little r, so these cancel, and then I've got plus big R, which will cancel that one, then plus little r plus big R, which will cancel that one, minus little r. So that in fact equals 0. So this tells me that if I take any point inside the sphere, then the net gravitational force on this point due to that sphere is 0. And so when we're considering the gravitational force on any point inside a sphere, it's only affected by the mass inside it, not by the mass outside of it, which kind of makes sense intuitively, because if we consider this point here, then this part of the sphere is closer to it. This part of the sphere is further away and has a force in the opposite direction. There's more mass on this part of the sphere, there's less on this part, but this part is closer. So you can see how those two effects could intuitively kind of balance each other out, but we have shown formally that they do completely cancel each other out.